Welcome to our deep dive into this fascinating world of prime numbers.
Oh, they're fascinating, all right.
We're going to be exploring a mystery that has baffled mathematicians for over 150 years, the Riemann hypothesis.
A real head scratcher.
It's kind of like a mathematical treasure hunt, and our map is John Derbyshire's prime obsession.
Great book.
It's packed with all sorts of intriguing puzzles and stories about these quirky geniuses who have tried to crack this code.
A lot of very interesting people involved in this, yeah.
So what I think is so intriguing about the Riemann hypothesis is that it revolves around something seemingly simple, prime numbers.
You know, these are numbers divisible only by one and themselves,
Yeah.
and they have just captivated mathematicians for centuries. It's amazing how long we've been looking at these things.
Yeah, I remember learning about prime numbers way back when, but I have to admit, I could use a bit of a refresher. Is there a quick way to explain why there's such a big deal in mathematics?
Well, I think the easiest way to think about it is that prime numbers are like the building blocks of all other whole numbers.
Okay.
They're like the atoms, if you will, of the mathematical world.
Ah, okay.
So understanding their distribution and behavior, it helps us unlock all these secrets about the structure of numbers themselves.
Okay, so it's not just about the primes themselves, it's about understanding the fundamental patterns underlying all numbers.
That's it.
That makes a lot of sense.
Yeah.
So, now, how does the Riemann hypothesis fit into all of this?
Well, the Riemann hypothesis, which was, first proposed by Bernhard Riemann, I think it was in 1859, it makes this prediction about where these prime numbers will sort of pop up along the number line.
Right.
So it's kind of like think of it like a blueprint for finding these elusive mathematical creatures.
Oh, that's pretty cool. I like that. But before we dive into the Riemann hypothesis, I was really intrigued by that card stacking puzzle you mentioned earlier.
Oh, yeah.
The one where you try to get a stack of cards to overhang the edge of a table as far as possible.
That's right. That's right. It's a really classic thought experiment, and it illustrates some of the concepts at the heart of the Riemann hypothesis.
Oh, wow.
Yeah, yeah. So let's say you have a deck of cards,
Uh-huh.
and you carefully stack them, You can get the top card to overhang the edge by half its length.
Okay.
Add another card, and you can push the stack out a little bit further. With 4 cards, you're already over a full card length.
Right, and then the more cards you add, the further you can kind of extend that overhang, right?
See, the idea
But what I found really surprising was how far you can actually push it.
is pretty wild.
Yeah, you said that with 52 cards, the overhang is more than 2 card lengths.
That's right.
And with 1,000,000,000,000 cards, it's what, over 14 card lengths?
Yeah, something like that.
It's insane.
Yeah, it's pretty remarkable, isn't it?
Yeah.
And this is where this concept of the harmonic series comes into play.
Okay.
The overhang lengths we discussed, 1/2, 1/4, 1/6, and so on. These form a series called the harmonic series.
Mm.
And it turns out that this series, it diverges, meaning that the sum of its terms grows infinitely large.
So even though each additional card is adding a smaller and smaller amount to the overhang,
Right.
the total overhang will eventually become infinitely large.
Right. Yeah.
So it's like you're squeezing infinity out of something finite.
Yeah. Yeah, exactly.
Hmm.
This puzzle, it really demonstrates, the power of infinite series and their, often counterintuitive behavior. And the harmonic series, it's interesting it diverges, but it had these intriguing similarities to the series in the Basel problem.
Oh, right.
And that one, unlike the harmonic series, that one converges to a finite number.
Wow, so you're telling me that there are these infinite series that can either explode to infinity or can neatly settle down to a specific value?
Yeah, that's basically it.
That's pretty wild. But how does all this relate to prime numbers and the Riemann hypothesis?
Well, the link lies in this mathematical function called the log function. This seemingly simple tool, it plays this really crucial role in understanding prime numbers.
Okay.
And as we sort of delve deeper into Riemann's work, you'll see how this log function helps us unlock the secrets of those, surprisingly large card overhangs and their connection to the distribution of prime numbers.
Okay, I'm starting to see how these seemingly disparate pieces fit together.
Yeah,
It's
yeah.
like a mathematical jigsaw puzzle.
Exactly.
But before we go any further, can we take a quick detour and just talk about Bernhard Riemann himself? He seems like a fascinating figure.
Oh, yeah, he's a remarkable guy. Riemann's story is one of incredible intellectual brilliance, but it's set against this backdrop of personal hardship.
Right.
Despite facing poverty and the loss of several siblings.
Wow.
He had this remarkable aptitude for mathematics from a very young age.
So it sounds like he had a tough childhood. Did those challenges influence his work at all, do you think?
Well, it's hard to say for sure, but his personal losses, they certainly impacted him. He was known to be very shy, very reserved, deeply devoted to his family.
Yeah.
And, his mathematical pursuits might have provided him with a refuge, I think.
Oh, okay. So while facing all these hardships, he's simultaneously grappling with some of the most profound mathematical ideas of his time.
Exactly, yeah.
That's quite a contrast. So where did this mathematical journey begin for him?
Well, it all began at the University of Göttingen.
Okay.
It was a very renowned center of mathematics in Germany at the time. And there, he had the opportunity to study under some of the greatest mathematical minds, including Carl Friedrich Gauss, considered by many to be the prince of mathematicians.
Wow. So that's like studying under Einstein if you're a physicist.
Yeah, pretty much. Pretty much, yeah.
What was the mathematical scene like in Germany during Riemann's time?
Well, 19th century Germany was just a hotbed of mathematical innovation.
Right.
Yeah. It was this time of real intellectual ferment, fueled by historical events like the Napoleonic Wars and educational reforms in Prussia.
Oh, wow.
This created just fertile ground for the growth of science and mathematics.
So Riemann was in the right place at the right time for a budding mathematician.
Definitely. He was very lucky.
What was his relationship like with Gauss?
Well, Gauss was this towering figure,
Right.
and Riemann held him in very high esteem. But Gauss was also known for being quite aloof, and sometimes critical.
Oh.
He often made these significant discoveries, but he didn't publish them,
What?
which led to conflicts with other mathematicians who independently arrived at the same results.
I can see how that would cause some tension.
Yeah, it did. It definitely did. Interestingly enough, though, Gauss played this pivotal role in guiding Riemann toward the path that ultimately led him to the Riemann hypothesis.
Really?
Yeah, when Riemann was preparing for his habilitation lecture,
Okay.
it was this crucial step towards becoming a professor. Gauss actually suggested that he tackle a topic related to prime numbers.
So it was Gauss's suggestion that set Riemann on the course to developing his famous hypothesis.
In a way, yeah. Yeah.
That's fascinating. But before we dive into that, you mentioned the Göttingen Seven earlier.
Right.
Who were they and why were they significant?
Well, the Göttingen Seven were this group of professors at the University of Göttingen.
Okay.
And they were actually dismissed from their positions back in 1837 due to their political views.
Really?
Yeah. They opposed the authoritarian rule of the King of Hanover, who had revoked the state's liberal constitution.
It sounds like Riemann was living and working in a time of some political turmoil.
Oh, absolutely.
Did this affect his mathematical work at all, do you think?
While Riemann was primarily focused on his research, he was undoubtedly aware of the political climate.
Yeah.
I mean, even his mentor, Gauss, was a member of the Göttingen Seven, and he faced consequences for opposing the king.
Wow. So even the Prince of Mathematicians wasn't immune to political pressures.
No one was immune. It was a difficult time.
This is adding another layer of depth to Riemann's story, I think. Okay, let's shift gears back to the mathematics a little bit. We were talking about the prime number theorem before we kind of delved into Riemann's life.
Right.
Can you remind me what that is?
Yeah, the prime number theorem, or PNT for short, it basically describes the average distribution of prime numbers.
Okay.
It gives us a way to estimate how many primes exist up to a given number.
Right, and we talked about how prime numbers become less frequent as you go further along the number line.
That's right, yeah.
But how does the PNT quantify that?
Well, the PNT states that the number of primes less than a given number, let's just call it n.
Okay.
It's roughly equal to n divided by the natural logarithm of n.
Okay.
So as n increases, the proportion of primes, it decreases, but this decrease is very gradual. And the PNT gives us this precise way to kind of measure this behavior.
So the PNT provides kind of a general roadmap for prime numbers, but what's the link between the PNT and the Riemann hypothesis?
Well, the PNT is a good approximation, but the Riemann hypothesis kind of goes further.
Okay.
It suggests that the errors in this approximation follow a specific pattern.
Yeah.
And it turns out this pattern is connected to the zeros of a complex function called the Riemann zeta function.
Ah, there's that zeta function again. It sounds like the Riemann hypothesis is kind of refining the PNT, offering this more detailed picture of how primes are distributed.
Yeah, exactly. It goes beyond that average behavior described by the PNT and provides insights into the subtle fluctuations.
Yeah. Oh, wow.
Yeah, in the occurrence of these prime numbers.
This is getting pretty deep. Before we jump headfirst into the Riemann zeta function,
Okay.
I'm curious about the historical context kind of leading up to Riemann's work.
Sure.
You mentioned a mathematician named Chebyshev earlier.
Right.
What role did he play in all this?
Well, Derbyshire was this brilliant Russian mathematician who made significant strides in the study of prime numbers in the mid-19th century.
Okay.
He was working on proving the prime number theorem,
Oh, wow.
and he developed important techniques for estimating the number of primes.
So he was essentially tackling the same problem that Riemann would later approach.
Yeah, exactly.
Wow.
Yeah, Chebyshev's work really laid the foundation for Riemann's groundbreaking insights.
Okay.
In fact, Riemann himself acknowledged Chebyshev's contributions in his famous 1859 paper on the zeta function.
It's fascinating to see how mathematical knowledge builds upon previous discoveries.
Oh, it always does.
It's like each generation of mathematicians adds a new layer to this grand intellectual edifice.
That's a beautiful way to put it.
Tell me more about Chebyshev's life. What kind of challenges did he face?
Well, Chebyshev's life is a testament to the power of intellectual curiosity and perseverance.
Mm.
He lived in Russia under Tsar Nicholas I. It was a period marked by political repression and limited academic freedom.
Wow.
But despite these challenges, he pursued his mathematical passions, making significant contributions to number theory, probability, all sorts of fields.
It's inspiring to hear how he thrived amidst such adversity. It speaks volumes about his dedication to mathematics.
Yeah.
You also mentioned something called Chebyshev bias.
Oh, yeah.
What's that all about?
Yes. Chebyshev's famous bias.
Yeah.
It's this curious phenomenon he observed while studying the frequency of primes.
Okay.
And he noticed this slight tendency for primes to be more likely to leave a remainder of 3 when divided by 4,
Oh, wow.
compared to leaving a remainder of 1.
That's really interesting. So even though prime numbers seem randomly distributed, there are these subtle patterns and biases that emerge.
Exactly.
Wow.
Chebyshev's bias highlights that even in the seemingly chaotic world of prime numbers, these hidden structures and patterns are just waiting to be discovered.
This is giving me a whole new perspective on prime numbers. They're not just these abstract entities. They're part of this complex and beautiful mathematical tapestry.
That's a great way to put it. Yeah, the study of prime numbers really reveals these intricate and often surprising connections that just weave through the fabric of mathematics.
Okay, I think we're finally ready to tackle Riemann's 1859 paper. What made this paper so groundbreaking, and how did it lead him to the Riemann hypothesis?
Well, Riemann's 1859 paper, it was titled On the Number of Primes Less Than a Given Magnitude.
Okay.
It's considered a masterpiece of mathematical thought.
Really?
Oh, yeah. It's remarkably short, very dense, and there are very few mathematical symbols in it.
Wow.
Yet within its pages, Riemann lays out this revolutionary approach to understanding prime numbers, and it has fascinated mathematicians ever since.
So it's like a mathematical treasure map packed with hidden insights.
You could say that. Yeah, it's a great analogy.
I like it.
Riemann's paper outlines this bold plan for exploring the distribution of prime numbers by connecting them to a complex function called the Riemann zeta function.
Okay.
And this connection, it's really the key to unlocking the secrets of the primes.
Okay, on the edge of my seat. Tell me more about this golden key. How does the zeta function relate to prime numbers?
This is where the real magic happens,
Okay.
Riemann discovered this remarkable equation that links the zeta function to an infinite product over all prime numbers.
Wow.
And this equation is known as the Euler product formula.
Okay.
It's like a bridge between the world of prime numbers and this whole realm of complex analysis.
Wow, that sounds incredibly profound. Before we dive into the specifics, can you remind me what complex numbers are and how they kind of fit into all this?
Yeah, complex numbers, they basically extend the familiar number line we learned in school to include numbers that involve the square root of -1. It's denoted by the letter I.
Right.
And they can be visualized on this two-dimensional plane called the complex plane, where each point represents a unique complex number.
Right, I vaguely remember complex numbers, but I have to admit I always found them a little bit mysterious.
Oh, they are? They are.
Why are they so important in the context of the Riemann hypothesis?
Well, because the Riemann zeta function, which is at the heart of the Riemann hypothesis, it's a function of a complex variable.
Okay.
This means that its input and output are complex numbers. And as Riemann discovered, The behavior of this function on the complex plane is intricately linked to the distribution of prime numbers.
Okay, so to understand the Riemann zeta function, we need complex numbers.
Yeah.
And to understand prime numbers, we need the zeta function. So it's this chain of interconnected concepts.
Exactly, yeah. Riemann's genius lies in bridging these seemingly disparate areas of mathematics and revealing those profound connections between them.
Okay, I think I'm starting to grasp the big picture here.
Right.
Let's zoom in on the Riemann zeta function itself. How is it defined, and what are these zeros that everyone keeps talking about?
All right, so the Riemann zeta function, it's denoted by this Greek letter zeta. It is, and it's defined as an infinite sum.
Oh, boy.
So for a given complex number, s equals the sum of 1 raised to the power of s plus 2 raised to the power of s plus 3 raised to the power of s, and so on, all the way to infinity.
Okay, I'm already getting lost.
It's a lot. It's a lot.
What's the significance of these zeros of the zeta function?
Well, the zeros of the zeta function, they're the complex numbers s for which s equals 0.
Okay.
These zeros, they hold the key to understanding the distribution of prime numbers. Riemann made this remarkable observation about these zeros. He noticed that they seem to lie along a specific vertical line in the complex plane. It's called the critical line.
So if we could find all the zeros of the zeta function and prove that they all lie on this critical line, would we have proven the Riemann hypothesis?
That's exactly what the Riemann hypothesis states. Yeah, if we can prove that all the non-trivial zeros of the zeta function lie on the critical line, we would unlock these really profound insights into the distribution of prime numbers.
This is getting exciting, but I'm still having trouble visualizing how the zeta function maps points on the complex plane.
It's tricky.
It's true.
Is there any way to kind of picture this?
Visualizing the Riemann zeta function can be very tricky.
Yeah.
It twists and turns the complex plane in all these fascinating ways.
Okay.
But one way to understand its behavior is to imagine an argument ant walking along different paths on the complex plane.
An argument ant.
Yeah.
I like this already.
As the ant walks, it carries a little display that shows the value of the zeta function at its current location.
Okay, I like this argument ant idea. It's a much more creative way to think about complex function.
It helps to have a visual, right?
Yeah, so how does this ant help us understand the zeros of the zeta function? Well, the argument ant, it helps us see that the zeta function sends specific points on the complex plane to 0. These points, the zeros of the zeta function, they're scattered throughout the complex plane.
Right.
And as Riemann observed, those non-trivial zeros, the ones that are most relevant to the Riemann hypothesis, they seem to cluster along that critical line we talked about.
So as the ant explores the complex plane, it's like it's mapping out the locations of these zeros.
That's it.
Like these hidden mathematical treasures.
That's a great way to think about it. But the question is, how do we actually find these zeros?
Yeah.
And how do we know if they lie on the critical line? Finding them is a very challenging task. It requires very sophisticated algorithms and powerful computers.
It sounds like we need some serious computing power to crack this code. So have we made any progress in finding these zeros?
Thanks to the work of brilliant mathematicians like Andrew Odlyzko, we now know the location of billions of zeta zeros.
Wow.
And they all lie on the critical line.
Billions of zeros, all line up perfectly. It's hard to believe that's just a coincidence.
Most mathematicians agree.
Yeah.
The overwhelming numerical evidence really suggests that the Riemann hypothesis is true, but evidence isn't proof. We still need this rigorous mathematical argument to definitively settle the matter.
So the hunt for a proof continues. What are some of the approaches that mathematicians are taking to try to solve this puzzle?
Well, there are many different avenues of attack, each drawing on different areas of mathematics. Some mathematicians are using tools from algebraic number theory.
Okay.
Others are exploring connections to geometry and topology. And then there are computational approaches that use very powerful computers to probe the behavior of the zeta function at unimaginable scales.
It sounds like a multi-pronged assault on one of the biggest mysteries in mathematics.
Yeah, that's a good way to put it.
Of all these approaches, there's one that really caught my attention, the Hilbert-Polya conjecture. Can you tell me more about that?
The Hilbert-Polya conjecture is one of the most tantalizing ideas in this quest to understand the Riemann hypothesis.
Okay.
It suggests that the zeros of the zeta function might correspond to the eigenvalues of a Hermitian operator, a concept from quantum mechanics.
Wait, quantum mechanics.
Yeah.
What does physics have to do with the Riemann hypothesis?
That's what makes it so intriguing, right?
Yeah.
The Hilbert-Polya conjecture, it proposes this bridge between the abstract world of number theory and the physical realm of quantum systems.
Okay.
So it suggests that the zeros of the zeta function, these seemingly ethereal mathematical objects, they might have this physical interpretation in terms of the energy levels of a quantum system.
So it's like the zeros of the zeta function aren't just these abstract mathematical entities. They're echoes of the quantum world.
That's the essence of the conjecture, yeah. And it opens up this whole new perspective on the Riemann hypothesis, suggesting that its solution might be found in the realm of physics.
This is all incredibly thought-provoking. I can't wait to hear more about this connection between the Riemann hypothesis and quantum mechanics, but I think we've covered a lot of ground today.
We have. It's been a good start.
Yeah.
Yeah. So before we kind of delve further into that connection with quantum mechanics, maybe we can do a quick recap of the Hilbert-Polya conjecture.
Right. It was all starting to make my brain feel a bit like one of those endlessly stacked card decks.
So in this case, think of a special kind of matrix.
Okay.
It's called a Hermitian matrix,
Okay.
and it has this really fascinating property. It's eigenvalues, specific numbers that are associated with the matrix.
Right.
They're always real numbers.
Okay. I remember you mentioning Hermitian matrices and eigenvalues before. Could you just remind me how those tie into the Riemann hypothesis?
Yeah, so the conjecture suggests that there might be this hidden Hermitian operator out there, somewhere in the vast mathematical universe, whose eigenvalues perfectly align with the non-trivial zeros of the zeta function.
So we're searching for this special matrix, a Hermitian one, whose eigenvalues match up exactly with the zeros of the zeta function. And if we find it, that could potentially explain those zeros in terms of a physical system.
Exactly, that's the hope.
This is all pretty mind-boggling. I'm still a bit hazy on the concept of eigenvalues. Could you give me a quick reminder?
Sure. Think of a matrix as like a machine that transforms vectors.
Okay.
So when you feed a vector into this machine, it spits out a new vector, right?
Okay.
Eigenvalues are these special numbers that are associated with the matrix, and they tell you how much the original vector is stretched or shrunk during that transformation.
Okay, that makes sense. So are we saying that if the Hilbert-Polya conjecture is true, the zeros of the zeta function are kind of telling us something about how a quantum system behaves?
Yeah, that's the exciting possibility.
Yeah.
It opens up this whole new way of understanding the Riemann hypothesis. Instead of just focusing on the abstract properties of the zeta function, we could potentially study a physical system that actually embodies those properties.
Yeah, I'm starting to kind of grasp how this conjecture could completely change our approach to the Riemann hypothesis. But I'm curious about where the idea originated. Who were Hilbert and Polya, and how did they come up with this connection?
Well, David Hilbert and George Polya, they were two brilliant mathematicians in the early 20th century.
Okay.
And they both made major contributions to many areas of mathematics,
Yeah.
Number theory, functional analysis, all sorts of things.
So they were really heavy hitters in the math world. Did they work together on this conjecture?
Well, the origins of the Hilbert-Polya conjecture are a bit of a mystery. It's thought that they both came up with the idea independently, but they never formally published it.
So it's like a mathematical whisper that's been passed down through generations of mathematicians.
Yeah, you could say that it was more of a suggestion, a spark of inspiration that has captivated mathematicians ever since.
I like that it really highlights the collaborative nature of mathematics. It's not always about individual brilliance, but also about sharing ideas and building upon each other's work.
Oh, absolutely. Mathematics thrives on that exchange of ideas.
Yeah.
And the Hilbert-Polya conjecture is a testament to that power of collaboration.
So we have this captivating conjecture that connects the Riemann hypothesis to quantum mechanics. But is there any evidence to actually back it up? Has anyone actually found this mysterious Hermitian operator?
Well, no one has discovered an operator that perfectly replicates the zeta zeros.
Okay.
But there have been some really encouraging developments. One of the most exciting clues emerged from this chance encounter between a young mathematician, Hugh Montgomery, and the renowned physicist, Riemann Dyson.
Oh, now this sounds like a story. Tell me more about this meeting of the minds.
Yeah, so back in the early 1970s, Hugh Montgomery was a graduate student at Cambridge University,
Okay.
and he was deeply engrossed in studying the Riemann's zeta function. He was particularly interested in the spacing between the zeta zeros, trying to unravel their statistical properties.
So he was looking for patterns in the way the zeros were arranged.
Exactly at the same time, Riemann Dyson was this leading physicist at the Institute for Advanced Study in Princeton, known for his groundbreaking work in quantum electrodynamics and other areas of theoretical physics.
So we have a number theorist and a physicist each working on these seemingly unrelated problems.
Right.
How did their paths intersect?
It was a chance encounter at a tea party at the Institute for Advanced Study.
Okay.
Montgomery was visiting Princeton, and someone introduced him to Dyson, and they just started chatting about their research.
Of course, as you do.
Right, and Montgomery, who was actually quite reserved,
Okay.
he hesitantly mentioned his work on the spacing of the zeta zeros.
Okay, I can picture these two brilliant minds sipping tea and casually discussing these really complex mathematical concepts.
Yeah, it's a great image.
So what happened next?
Well, Montgomery had discovered this peculiar pattern in the distribution of the zeros,
Okay.
but he couldn't really explain it.
Hmm.
He'd even developed this formula that captured this pattern, but he was really puzzled by its meaning.
So he had the pieces of the puzzle, but he couldn't quite put them together.
Yeah, that's a great way to describe it. He needed a key to unlock the secrets of his formula, and that key was about to be handed to him by Riemann Dyson.
Okay, now I'm really intrigued. Tell me, how did Dyson react to Montgomery's discovery?
Well, Dyson, with his really deep understanding of both mathematics and physics, he instantly recognized the significance of Montgomery's formula.
Wow.
And he exclaimed, "That's the pair correlation function for the eigenvalues of random Hermitian matrices."
Hold on. He recognized a formula from number theory as something from quantum mechanics.
Exactly. It was an incredible moment.
That's incredible.
Yeah, Dyson had encountered the same statistical distribution in his work on the energy levels of complex quantum systems. So this chance meeting really sparked a flurry of research connecting the Riemann hypothesis to this fascinating world of random matrices and quantum chaos.
Wow. It's like the universe was trying to tell mathematicians a secret through the language of physics.
That's a really poetic way to think about it. But Montgomery and Dyson's encounter, it really opened up this whole new chapter in the study of the Riemann hypothesis. It suggested that the key to understanding the distribution of prime numbers might actually lie in the statistical properties of random matrices, which in turn are connected to the behavior of quantum systems.
So even though no one has yet found this specific Hermitian operator that explains the zeta zeros, this statistical connection to random matrices kind of provides strong evidence for the Hilbert-Polya conjecture.
Exactly. It's this remarkable piece of the puzzle that really reinforces this belief in a deep connection between mathematics and physics.
Yeah, this is also mind-blowing. Now, tell me more about these random matrices. What are they and how do they actually relate to quantum systems?
Well, random matrices, as you might guess, are matrices whose elements are randomly chosen.
Okay.
They might seem like mathematical curiosities, but they have these really profound connections to various areas of physics, including quantum mechanics.
Okay, so they're more than just random numbers in a grid. How do they actually play a role in the quantum world?
Well, in quantum mechanics, we describe physical systems using these mathematical objects called operators.
Right.
And these operators are often represented by matrices.
Okay.
And they act on quantum states, which are also represented by vectors.
So we're kind of using matrices as a sort of language to describe how quantum systems behave.
Yeah, you got it.
Okay.
Now, when we study complex quantum systems like atomic nuclei or large groups of interacting particles,
Right.
we often encounter operators that are represented by these very large matrices.
Okay, but where do the random matrices fit into all of this?
Well, when you're dealing with these really massive matrices, it's practically impossible to know all of their exact elements.
Right, of course.
So we use random matrices to model their statistical properties.
So it's like saying we don't know all the details of this quantum system, but we can use these random matrices to capture its overall behavior.
Exactly. And surprisingly, these random matrix models have been incredibly successful in describing the statistical properties of a variety of quantum systems.
It's amazing that we can use randomness to understand the complexities of quantum systems. It seems counterintuitive. But you're saying the statistical properties of random matrices have really proven to be these powerful tools in quantum mechanics.
That's right. But how does this all tie back to the Riemann hypothesis?
Yeah, that's what I'm wondering. We've talked about random matrices and quantum systems, but how does that connect back to the world of prime numbers?
Well, the connection lies in the statistical properties of the eigenvalues of random matrices.
Okay.
Remember Montgomery's discovery.
Right.
The spacing between the zeta zeros followed this particular statistical distribution.
Right.
Dyson recognized this distribution as the same one that describes the spacing between the eigenvalues of certain types of random matrices.
Wow, so the zeta zeros and the eigenvalues of random matrices are basically playing the same tune, even though they come from these completely different areas of mathematics.
Precisely. It suggests this really deep underlying connection between the way prime numbers are distributed and the statistical behavior of quantum systems.
This is truly remarkable, but how can we be sure that the zeta zeros and the eigenvalues of random matrices have the same statistical distribution? It's
Yeah.
not like we can just look at them and see a resemblance.
Right. This is where the power of computation really comes into play.
Okay.
Mathematicians have developed these sophisticated algorithms, and they've used powerful computers to calculate billions of zeta zeros
Wow.
and compare their spacing to the eigenvalues of random matrices.
So we have solid numerical evidence to support this connection.
Yeah, the numerical evidence is overwhelming.
Wow.
It shows this remarkable similarity between the statistical properties of the zeta zeros and the eigenvalues of certain random matrices.
This is really groundbreaking stuff. It feels like we're peering into the hidden architecture of the universe and discovering these unexpected links between these seemingly unrelated concepts.
That's the beauty of mathematics. It reveals the underlying patterns and connections that govern our world, often in surprising and awe-inspiring ways.
Yeah, I'm completely hooked on this story. Now, tell me more about the computational work that's been done. Who are the key players in this field, and what have they actually discovered?
One of the pioneers in computational work on the Riemann hypothesis was Andrew Odlyzko, a mathematician at Bell Labs back in the 1980s. He used supercomputers to calculate millions of zeta zeros to this very high degree of precision.
Wow. So Odlyzko was crunching numbers on a scale that Riemann could only have dreamed of.
Absolutely. His work provided further evidence for this connection between the zeta zeros and random matrices.
It sounds like Odlyzko's work really significantly bolstered the credibility of the Hilbert-Polya conjecture.
Yes, his computational findings gave mathematicians even more confidence that they were on the right track in their quest to unravel the Riemann hypothesis.
Yeah, it's really inspiring to see how human ingenuity and collaboration can really drive scientific exploration. Now, what are some of the challenges involved in this computational work? I imagine calculating the zeros of the zeta function is no walk in the park.
You're absolutely right. Calculating zeta zeros to high precision is a very computationally demanding task.
Yeah.
It requires sophisticated algorithms, powerful computers, and a healthy dose of patience.
Yeah. What are some of the specific hurdles that mathematicians face?
One major challenge is the sheer volume of zeros that need to be calculated.
Right.
The zeta function has an infinite number of zeros, so mathematicians have to focus on calculating a subset of them, usually those with imaginary parts, up to a certain value.
It's like trying to map an infinite landscape one small section at a time.
That's a good way to put it. And the further you venture out into the complex plane, the more difficult the calculations become.
Yeah, I can imagine it's like trying to capture a clear picture of a distant galaxy. The farther away it is, the more powerful your telescope needs to be.
Exactly. And in mathematics, our telescopes are powerful computers and sophisticated algorithms.
Right, so we need some serious computational firepower to tackle this problem. Are there any other challenges besides just the complexity of the calculations?
Yeah, another challenge is the need for extreme precision. To accurately compare the statistical properties of the zeta zeros to the predictions of random matrix theory, we need to calculate those zeros to many, many decimal places.
So it's not just about finding the zeros, it's about finding them with incredible accuracy.
Precisely. And as you go further out in the complex plane, the required precision increases.
This is starting to sound like a mathematical Mount Everest. It's this daunting challenge, but the rewards for conquering it are immense.
That's a great analogy. The Riemann hypothesis is one of the most challenging problems in mathematics, but solving it would unlock these profound secrets about the distribution of prime numbers and their connection to the very fabric of the universe.
Yeah, you've convinced me that the Riemann hypothesis is a pursuit worthy of our greatest minds. Now, shifting gears slightly, you mentioned chaos theory earlier.
Right.
Can you elaborate on how chaos theory relates to the Riemann hypothesis?
Well, chaos theory is this branch of mathematics that studies systems that are extremely sensitive to their initial conditions. And these chaotic systems display unpredictable and seemingly random behavior, even though they're following deterministic rules.
Right. It's like that butterfly effect.
Yeah,
You know, a butterfly flapping its wings in one part of the world can trigger a hurricane on the other side.
That's a classic example of chaos, and it turns out that chaos theory may have something to say about the Riemann hypothesis.
Okay, now this is blowing my mind. How could chaos theory possibly be connected to the distribution of prime numbers?
The connection stems from the work of Michael Berry, a physicist, who has made significant contributions to the study of quantum chaos.
Okay.
Back in the 1980s, Berry proposed that the Riemann zeta function could be viewed as a model for a chaotic system.
So he's suggesting that the seemingly random behavior of the zeta zeros might actually reflect this underlying chaos?
Precisely. Berry argued that if the Hilbert-Polya conjecture is true, meaning the zeta zeros correspond to the eigenvalues of a Hermitian operator, then that operator might describe a chaotic system.
So maybe prime numbers are dancing to the beat of chaos after all.
That's a very poetic way to put it. Berry's work suggests that the distribution of prime numbers might not be as random as it appears. There might be this hidden order, this chaotic order lurking beneath the surface.
This is all incredibly intriguing. We're uncovering layer upon layer of complexity and beauty in the world of prime numbers.
That's the beauty of mathematics. It reveals the hidden connections and patterns that govern our world, often in surprising and awe-inspiring ways.
Yeah, I'm completely engrossed in this journey, but I think we've reached another natural stopping point. Maybe we can let all this information sink in and then continue our exploration of the Riemann hypothesis and its profound implications in our next part. Welcome back to our deep dive into the Riemann hypothesis. We've been exploring some really fascinating connections between prime numbers, quantum mechanics, and even chaos theory.
It's quite a mix.
It's mind-boggling to think about how these seemingly different areas of math and physics might actually be intertwined.
Yeah, it really highlights the interconnectedness of knowledge.
Yeah.
And, these connections really hint at this deeper structure governing the behavior of prime numbers.
Yeah.
Perhaps their distribution isn't purely random, but it's actually influenced by some hidden order, possibly rooted in quantum mechanics.
You mentioned Alain Kohn earlier.
Right.
He's working on this very abstract approach to the Riemann hypothesis.
Yeah.
Using something called Adelic spaces.
That's right.
What exactly are Adelic spaces and how do they relate to the Riemann hypothesis?
Adelic spaces are quite an advanced mathematical concept. Essentially, they provide a way to combine information about all prime numbers into a single mathematical object.
So it's like a master blueprint containing everything there is to know about prime numbers?
That's a good way to think about it.
Yeah.
Alain Kohn, a brilliant mathematician who's renowned for his work in non-commutative geometry, he believes that Adelic spaces might be the key to actually constructing a Riemann operator, that elusive Hermitian operator we talked about earlier.
Okay, so Kohn is trying to build a Riemann operator that acts on this Adelic space, which holds all the secrets of prime numbers if he succeeds. Could this operator unlock the Riemann hypothesis?
That's the hope.
Wow.
Kohn's approach is incredibly ambitious and complex,
Yeah.
drawing on deep connections between number theory geometry and quantum mechanics.
It's like he's building this bridge between the abstract world of prime numbers and the physical world of quantum systems. But honestly, this concept of Adelic space, it's pretty daunting. Is there any way to understand it on a more intuitive level?
Maybe we can try an analogy. Imagine you want to describe a city.
Okay.
You could talk about its streets, buildings, parks, and so on.
Right.
But you could also describe the city through the experiences of the people who live there, their stories, their interactions.
So instead of just listing physical features, you're kind of capturing the city's essence through its human element?
Yeah, that's the idea. Adelic spaces do something similar with prime numbers. They describe primes not through their individual values, but through their relationships with all other primes, like this vast interconnected network.
So it's a way to see the bigger picture, the web of connections that makes prime numbers so fascinating.
Exactly. And this network, this Adelic space, it might hold the key to finally understanding the distribution of prime numbers and proving the Riemann hypothesis.
It's all pretty mind-blowing, but you mentioned that opinions are divided on Kohn's work.
Right.
Why is that?
Kohn's approach is very abstract and very complex, and some mathematicians are skeptical that it'll lead to a proof of the Riemann hypothesis.
Okay.
They argue that he's essentially just replaced one incredibly difficult problem with another equally difficult problem.
So it's like climbing Mount Everest by choosing a different path, but the mountain is still just as tall?
That's a good analogy.
Yeah.
However, even if Kohn's work doesn't directly lead to a proof of the Riemann hypothesis, it's pushing the boundaries of mathematics and opening up all these exciting new avenues of exploration.
Yeah, it's inspiring to see these mathematicians venturing into uncharted territory with such boldness and creativity.
It really is. Okay, now shifting gears a bit, you mentioned this model developed by Harold Kramer.
Right.
That treats prime numbers as essentially random. Can you tell me more about that?
Yeah.
Harold Kramer was a Swedish mathematician who developed this probabilistic model for the distribution of prime numbers.
Okay.
His model suggests that primes behave as if they were scattered randomly along the number line with their average density dictated by the prime number theorem.
So it's like flipping a coin to decide whether a number is prime or not.
It's a simplified way to think about it, but it captures the essence of Cramer's model. It suggests that there's this random element to the occurrence of prime numbers.
But we've been talking about all these hidden connections and structures underlying prime numbers. How can they be both random and structured at the same time?
It's a paradox, isn't it? Cramer's model acknowledges the randomness of prime number distribution, but it still allows for underlying patterns and biases.
So it's like a painting where the individual brushstrokes appear random, but there's an overall composition, a deliberate structure guiding the artist's hand.
That's a perfect analogy. Cramer's model proposes that prime number distribution might be this delicate balance between randomness and order.
This is fascinating. Is there any evidence to support Cramer's model? Does it accurately predict the behavior of prime numbers?
Well, Cramer's model has been successful in explaining certain aspects of prime number distribution.
Okay.
However, it's not a perfect model.
Right.
There are these known discrepancies between its predictions and the actual behavior of prime numbers.
So it's a useful tool, but it doesn't capture the complete picture.
Exactly, and this is where the Riemann hypothesis might come in.
Okay.
Mathematicians believe that if the Riemann hypothesis is true, it could provide this deeper understanding of the interplay between randomness and structure in the distribution of prime numbers.
So the Riemann hypothesis could refine Cramer's model and give us this more accurate understanding of prime number behavior.
Precisely, it's like having this more powerful lens to examine the intricate landscape of prime numbers.
This is all incredibly exciting, but I'm wondering about the practical consequences of proving or disproving the Riemann hypothesis. Would it impact our everyday lives at all?
Well, it's a question that often comes up.
Yeah.
Well, the main motivation for studying this problem is intellectual curiosity.
Yeah.
There are these potential practical implications, particularly in cryptography.
Cryptography, the science of secure communication.
Exactly. Many modern encryption algorithms rely on the properties of prime numbers, and a deeper understanding of prime number distribution, something the Riemann hypothesis might offer, could lead to more secure encryption methods.
So proving the Riemann hypothesis could help us protect our online transactions and keep our digital secrets safe.
It's a possibility, however. The practical implications are still a bit speculative. The primary value of the Riemann hypothesis really lies in its deep mathematical significance and its potential to unlock all these new areas of mathematical understanding.
It's amazing how this problem that seems so abstract could potentially have real-world consequences.
That's often the case with fundamental scientific discoveries. They may appear purely theoretical initially, but they often lead to these unexpected technological advancements.
I'm convinced that the Riemann hypothesis is a problem worth pursuing, both for its intellectual beauty and its potential applications. What's the current status of research? Are we any closer to a solution?
Well, the Riemann hypothesis remains one of the biggest unsolved problems in mathematics. Despite the efforts of brilliant minds over the past century and a half, it continues to resist a definitive solution.
So it's still this mathematical Mount Everest waiting to be conquered.
You could say that, however, we've made substantial progress. We've uncovered these deep connections to other areas of math, including complex analysis, quantum mechanics, chaos theory. And with powerful computers and these advanced algorithms, we're exploring the behavior of the zeta function on this unprecedented scale.
It sounds like we're getting closer even if the summit remains elusive.
That's a good way to put it. Yeah, the Riemann hypothesis, it's a testament to human curiosity and this persistent quest for knowledge. It's a problem that has captivated mathematicians for generations and will likely continue to fascinate for many years to come.
Well, this deep dive into the world of prime numbers and the Riemann hypothesis has been an incredible journey. It's a story of intellectual brilliance, perseverance, and the unexpected connections that just weave through the fabric of knowledge. Who knows, maybe one of our listeners will be the one to finally crack this age-old code.
That would be a remarkable achievement. But even if the Riemann hypothesis remains unsolved for another century, the quest to understand it will continue to enrich our understanding of mathematics and its really profound connection to the universe.
Well, thank you for joining us on this fascinating exploration. We hope this deep dive has sparked your curiosity and left you with this sense of wonder about the power and beauty of mathematics.
Remember, there's always more to discover. Keep exploring, keep asking questions, and who knows what incredible discoveries you might make.